Okay, so let's go over a few problems from energy conservation. So the first one that we can look at is number 32 from chapter 5. And the givens here for this one, well, first off, the problem is about a pole vaulter and jumping over a certain height. And the actual question asks for what is the height that the pole vaulter will cross the pole at. So actually the height is over the pole. And so if we look at our givens, they give us the mass of the pole vaulter. They give us the initial velocity of the pole vaulter. They give the speed above the bar, so how fast is going above the bar, and it asks for the altitude. So we're looking for h. So if I set this up as energy conservation, I'm going to say my mechanical energy initial, so not is equal to my mechanical energy final. So at the very beginning, the pole vaulter has no gravitational potential. So the whole system's energy at the beginning is just kinetic energy. So we would have 1/2 m v initial squared. So the second part, though, the mechanical energy, there would be potential and there's kinetic because there's a velocity that the pole vaulter has on top. So in this case, we're going to have 1/2 mv squared plus mgh. And it's kind of nice here that since there's an m on everything, the m's actually cancel out. And now we are left with algebra problem on solving for h here. So what we would have is 1/2. I can factor out the 1/2 and say v0 squared minus v squared. So that's just subtracting this to this side. And then I would have it all divided by g. And that would give me my height. Okay, so let's look at the next problem. Next problem is really similar to this. So this problem is number 33. And in this case, we have a child in a sled with a combined mass of 50 kilograms slide down a slope. If the sled starts from rest and has a speed of 3 meters a second at the bottom, what is the height of the hill? Okay, so our givens again, let's go through and write those out. So we're given the mass of the child in the sled. The sled starts from rest and has a speed of 3 meters a second at the bottom. So the initial speed is 0, and the v at the bottom is 3 meters a second. So what's the height of the hill? So what is the height? So again, we're going to use conservation of mechanical energy. We're going to use a not there. Is equal to me final. Well, at the very beginning, the conservation of energy is just mgh. And at the end, it's 1/2 mv squared. So again, the masses cancel out. We didn't even have to have the mass in here. And so we're solving for we're solving for h. So h would just be equal to 1/2 v squared divided by g. Okay, so two pretty straightforward mechanical energy questions. So let's look at the next question, which is 34, sorry. So 34, we have a light spring, unstretched length of, so a spring, the unstretched spring has a length of 35 centimeters. So I'm going to call that x naught, 35 centimeters. So this is let's list our givens. Attached to a door frame and a 75 kilogram object is hung from the other end. So we know that the mass of this this object, and we'll call that m. So our givens are m, x naught, and the stretch spring, so x is equal to 41.5. Well, let's just keep it in variable form. So we have after the spring is stretched, so after that we have this x value. The x value would actually be from the very top down. So we have that this x. Okay, so it asks for a, find the spring constant. So the spring constant, we're actually going to use Hooke's law. So we have F is equal to negative kx, but the force here is due to, like, what's stretching this is the weight of the mass. So in this case we have mg is equal to negative kx, and so solving for the spring constant then, and then the x, so this negative here, spring constant will never be negative. So the x, the stretch of the x, this just says that the force is opposing the direction of kx, this restorative force. So I'm just going to say k is equal to mg over x, and I should be more specific here. So this x value is my delta x, because we only care about how much it's stretched. So we only care about this value right here. So to find that value, it's x minus x0. So we would have mg x minus x0, and that was giving my spring constant. Okay, so for part B asks for the load and the spring are taken down. The two people pull in opposite directions on the ends of the spring, each with a force of 190 newtons. Find the length of the string in this situation. So in this case, since we already found out k, now we have a new force, which I'll just put a number in here. They say 190 newtons, which is kind of interesting that if this force was 190 newtons, then because of Newton's third law, even if you're pulling 190 newtons from both directions, the force is still just going to be 190 newtons. So the spring only undergoes 190 newtons of force because of Newton's third law. So alright, we knew k from above. So now if I use F equals kx, F equals, we'll say negative kx, then x is equal to F over negative k. And that would be my my distance stretched. And that negative again just symbolizes that the x, the distance stretched, is in the opposite direction as the force. So we have to put that negative there. And that will give you your final answer. Okay, hope this helped.